In this session, we'll see the what is the phase shifting star delta transformer connection for positive sequence network and the negative sequence, the components. Phase shifting star delta transformer. Positive and negative sequence voltages and the currents, they are undergoing a phase shift in passing through a star delta transformer, which depend upon the labeling of the transformer. That is what you mean is here, that is a positive and negative sequence voltages and currents. If you are moving from star connection to delta connection, there is a phase shift. It is not, they are not in the same phase, because if the one side is star connection, the other side is delta connection, then the positive sequence current, if you are referring to star side, has got a different phase shift in the delta side. That what we are calling is the phase shift. Similarly, it is applicable to the voltage and the current. Therefore, the transformer ends marked with the dot have the same polarity. That is, I am taking a simple two winding transformer here. There is a dot convention. You are already aware of this dot convention. This transformer ends marked with the dot have the same polarity. That is, these are having the same polarity. Means at any given instant of time, this particular point has got higher potential. At the same time, this dotted line also has got a high potential with respect to other winding. That is the dot convention we have got. Then usually the high voltage side of the transformer is usually marked with H and H dash. That is, H and H dash is the terminology they are, or a nomenclature they are using to mark the high voltage winding. Therefore, the voltage in the high voltage winding is the written as VH dash, means H has got higher potential compared to H dash. That is dot convention what we are mean here is. Similarly, the low voltage side usually the marked as LR dash, or sometimes IEEE standards suggest it is X, X1, X2 like that. But here I am taking to make it very clear, that is high voltage and low voltage winding. Therefore, it is HH dash and it is L dash. And the currents I1 and I2 with directions of flow as indicated in figure are in same phase. That is, it is a incoming current, it is a outgoing current. They are in same phase because they are, one is entering into the dot, the other one is the leaving into the dot. This is how you have to mark the high potential of the transformer with its dot convention. Then I have to draw the star connection and the delta connection with the same potential or in phase the windings. Just you have to observe here, just I want to draw first a star connected the primary and delta connected secondary with one limb at a time or one phase at a time. First I am drawing here R phase, it has got higher potential with respect to another terminal. Okay, then the another one side I am taking this as considering as star connection. Just I am building a star connection here delta connection. It is also has got a dot convention here. It has got a higher potential with respect to this. Now I am adding to this a Y phase or a B phase. Here you can see here this terminal, that is the dot terminal, has got higher potential with respect to this point. At the same time, parallel to this, I am adding to the delta connection here. Just I am drawing here, that is which is parallel to this, that is here. This is once again, it has got higher potential with respect to this. It is same as this. Then I am adding one more phase here. It has got higher potential with respect to this. The same parallel I am adding to here to the delta connection here. Can look into, it has got higher potential with respect. Same as this, but it is a star connection. It is a delta connection. And I am marking the phase as ABC and secondary as here also ABC as the delta connection with a lowercase I am using ABC as the phase sequence in the case of the secondary, that is in the delta connection, and the uppercase ABC I am using for the marking the labels on the star connection. Then what is the phase shift in the positive sequence and negative sequence component, that we'll see. Okay. Now first I am drawing here the star side, the positive sequence component of the voltages. That is VAN1, VBN1, VCN1. All these are the positive sequence component of phase A, B and C on star side and B side. And here I am using here a subscript AN, means it is the phase value. That is VAN1 is the positive sequence component of phase A per phase. VBN1 is the positive sequence component of voltage B per phase, and it is a positive sequence voltage of phase C, it is per phase. That is, these are the phase values of VAN1, VBN1 and VCN1. Then if I am interested in the line voltage, that is, you can call the voltage between A and B, that is a line voltage between A and B. Then how we are finding out the line voltage between A and B? That is VAN minus VBN. That is VAN minus VBN gives the VAB. VAB, that is line to line voltage in the star connection. Therefore, what I have to do is, to VAN1 I have to add minus VBN1, so that VBN1 can be produced in the reverse direction. Therefore, you can see here, this is minus VBN minus VBN1 plus VAN1. If you are adding these two, then what I am getting is, it is VAB1, that is the line to line voltage between A to B in the star connection. That is what I am getting is, it is VAB1. Then if you are seen in the previous here, when if you are looking into this, that is between this point and this point, it is VAN1 in the star side, whereas between these two it is small ab. Small ab means it is a line to line voltage. Just I will complete this figure, you can see here. That is, what is the voltage between this and this point? It is VAN1. If you are looking into the positive sequence voltage, it is between this point and this point, it is VAN1. Whereas in the secondary side, it is also in phase with this, because both are drawn parallelly. You can see both are drawn parallelly. If you are measuring between this point and this point in the star side, that gives the VAN1 in the star side, whereas if you are measuring the voltage between these two, that gives, what is that? VAB, that is a line to line voltage. Means what I mean here is, VAN1 and VAB are in same phase. That is, VAN1 of the star side is the same as it is VAB on the secondary side or a delta connected side. What I mean is, small VAB is in phase with VAN1 of the star connection. Therefore, you look into here, this is VAB1. I told you that is small VAB1 is in phase with VAN1. Therefore, small VAB1, that is, it is a line to line voltage of the delta connected. VAB1 is line to line voltage of the delta connection. That is, you can see once again here, it is the voltage VAB1, it is in phase with VAN1. The same thing I shown here, that is VAB1 and VAN1, they are in phase. Then if you are comparing the star connected, the line voltage of the positive sequence on the star side and the line voltage on the the delta connected side, that is small VAB1, lowercase VAB1, there is a phase displacement of 30 degree. In other words, that is the star connected positive sequence line to line voltage leads its delta connect line to line voltage by an angle of 30 degree. That is how it is 30 degree. That is the star side VAB1, that is line to line voltage, is leading the delta connected positive sequence voltage by an angle of 30 degree. That is the what we are calling is the phase shift in the case of positive sequence component. Next, then similarly I am starting with the negative sequence of the vector diagram here on the star side. That is, here the phase sequence is A, B and C here. That is, the sequence is same as the original phasors. Here the sequence is changed. You can observe here it is A, C and B. A, C, B, because it is a negative sequence. Whereas VAN2, VCN2 and VBN2 are negative sequence component of phase A, C and B. Once again, I am interested in the line to line voltage on the star side. Once again, VAB2 is equal to VAN2 minus VBN2. That is VAN2 minus VBN2. So that what I have to do, VBN2 I have to produce in the negative direction. Then I am adding to VAN2, so that what I am getting is VAB2. See, here it is minus VBN2. This VBN2 is added to VAN2, so that what I am getting here is VAB2. This is line to line voltage in the star connection. Then you have seen that is VB of a delta connection and VAN, they are in same phase. That you can refer back here, thus and thus, that is VAB is thus and VAN2 is this, VAN2 across this and VAB2 across this. These are in phase, these two are in phase. Therefore, we can look into here, that is VAB2 is the line to line voltage, that is the positive negative sequence voltage of the star side. Then VAB2, that is a lowercase VAB2, is in phase with VAN2. That is VAN2. That is a line to line voltage in the delta connection. Because VAN2 and VAB2 are in phase that I shown you. They are in the parallel. Therefore, if you are observing the line to line voltage of the star side and the delta side here the star side line to line voltage of the negative sequence component lags the delta connected line to line voltage by an angle of 30 degree. That is lags an angle of 30 degree. That is, this is 30 degree. You can see here. It is 30 degree. Means in the negative sequence, line to line voltage in the star connection side lags the delta side by an angle of 30, whereas in the positive sequence, that is the line to line voltage in the star leads delta connected line to line voltage by an angle of 30 degree. That is what we are calling as the phase shift in star delta transformer for positive sequence voltages and current and the negative sequence voltages and the current. That is same statement I am writing here. Star side quantities lead delta side quantity by an angle of 30 degree. That is, star side quantities lead the delta side quantities by 30 degree, whereas negative sequence quantities, here the delta side quantities lead star side quantities by 30 degree, or star side quantities lags delta side by 30 degree. That is one and the same. This is what we are calling as the phase shift in star delta transformer.